Greetings and welcome to a new video about control system topics. We have so far discussed about stability, design of a controller in other videos using root locus method and also the root Hurwitz stability criterion. Another topic which is very important is the steady state error and also the sensitivity of your system to a specific parameter. We will in this video describe these in great detail, and we will also give you illustrated examples to make the situation even more clear. So let's look at our situation. Of course, we would like to step by step work out the calculations and also do the simulations in MATLAB to verify our calculations. What we have for this video in our first part is the theory. So we will describe the theory and also give you some background information to illustrate that in great detail. And in part 2, I will only focus on some examples. So the part 1 will be first about test signals. So what kind of test signals do we have in control systems specifically? We also talk about the steady state errors, then for the unity-gain feedback system configuration. Now in that case, you can do that using the closed-loop system transfer function, TS, or you can do that also using the loop gain transfer function, LS. So there are two methods to work out these steady state errors. This will be clarified in great detail shortly. Then we will discuss about the static error constants and also the type of your system. Now we will give here an example. I will call that example A. Then we will move on to the steady state error for disturbances, because these topics are all for a reference input, but we have also disturbance, which is the unwanted signal from outside. And again, we give an example to illustrate that concept in great detail. In addition, we will talk about the steady state error for non-unity-gain feedback system configurations, because most control systems are not unity-gain feedback in not unity-gain feedback configuration. So we need to also tackle those configurations. And also we'll discuss about sensitivity, which is a really important topic, and we will also give an example there to illustrate the concept. In part 2, we will specifically dive in the examples, and I will give 3 examples to illustrate also what we have discussed here in more detail. So this complete video will give you a nice, I hope, a nice overview of what steady state error is, including the sensitivity and some illustrative examples to move on with great detail about the calculations. So the part 1 of the theory, as I said. So before we move on to the theory, let's first look at a very generic problem or generic situation of a position control. Now this is a very classical way to illustrate that. We have a potentiometer here, which will then transform your desired angle to a voltage, and then that will then go to the motor and also be applied to our antenna, such that you can say, okay, I have applied here at 10 degrees as my desired angle, so that's my input command, and I would like to have also 10 degrees, of course, at my antenna. Now, if there is some error in that command and the actual output, that is the steady state error what we are talking about. Now, if you move on and look at it in great detail in a schematic form, you will have this. This is your desired angle command. This will be then converted to a voltage using this potentiometer that will go to the differential amplifier and then a power amplifier combined that will then process the signal, and then to the motor itself, and then this all models this antenna as a load and also the friction here, and that will be then give you your output angle. I won't go to in great detail here. It is my objective here to illustrate the steady state error. I would like to just mention here that this is a really classical problem about the position error. So if we move specifically to the block diagrams, we can say this angle what we here have as a desired angle, which is our command, which we require, the angle at the output must follow this angle. And if that is the case, then we have 0 steady state error, If it's not the case, then there is error, what we call the steady state error. So we will then focus on that specific case. All right, now let's then first look at the first topic, which is then test input signals. Now, for the definition, steady state error is the difference, again, between the input and the output for a prescribed test input. And that goes then in steady state for time up to infinity. So this is then mathematically defined in this form. Yeah, your system must be stable in order to have a calculation about the steady state error. Otherwise, it is meaningless because the system will then blow up and there's absolutely no constant error in your system response. These are the waveforms we see or we encounter in control systems frequently. So we have the step, and that's the waveform, and it is used for constant position measurements. And the time function is just 1. And the Laplace transform, we know that from the Laplace transform table, which is 1 over s. We also have another waveform, which is shown here as a linear increasing waveform, which is called a ramp. And it is a physical interpretation of that is the constant velocity. And that is in time domain given by t. And if you convert that to the Laplace transform, that will give you 1 over s squared. We also have a standard parabola, which is a second order expression. So we have this input that will give you as a physical interpretation the constant acceleration. Now, in order to go actually from here to there and then move back, this half is placed here as a coefficient. So it is 0.5 times t squared. And that will give you nicely, if you convert that to Laplace transform, 1 over s cubed. So you can always check this by differentiating this, and you will go back here, and if you differentiate this, you will go back there. This maybe also what you have encountered in the physics classes, that you have the acceleration, then the velocity, and then your position. All right, so these are the testings we will use and we will encounter in most of the time in control systems. Of course, you have also the sinusoidal, pure sinusoidal waveform that will give you then the frequency response of your signal, but that is not really interesting for us at the moment for steady state error calculations. Okay, now this is then a graphical representation of what can we do or what is meant by constant position, constant velocity, and also constant acceleration. So we have a tracking system here that will then track the location of your satellite in some orbit specifically, which is then constant with respect to the location here on Earth. It can be that your satellite has some velocity with respect to your location on Earth. That will be then a constant velocity. And also a missile may be another object that can have some acceleration, and then you are interested more specifically in acceleration than position or velocity. So these are all examples of the test signals that we can use. So step input represent constant position, again ramp input, so this linear increasing represent our constant velocity, and our parabola, standard parabola here, is then input for constant acceleration. Now these are our bases we will use later for our calculations. So let's first then look at the steady state error for unity gain feedback systems. Now we can use the closed loop transfer function for those calculations. So that is shown here in A. You can see the T, which is our closed loop transfer function, the reference here again, our error. So that is redrawing from the standard form. Now error between the input and output is always given here as shown. So the error is equal to the reference minus the output. So you actually calculate the difference. For the closed loop transfer function, we have this expression. This is always valid. So closed loop transfer function is the output divided by the input, and that can be also written in this form. So output is equal to the transfer function times the input r. Now, if we now combine these two expressions, so the closed loop transfer function and also expressed in the output and also the error, you have this expression in terms of the error at the left side and also the others on the right side. If we rewrite this and also check the final value of that using the final value theorem. You can say, okay, the final value of this one in time domain is given by this, so the limit t approaching infinity of that in time domain is also equal to limit s approaching 0, then s times this expression. That means then the following. We have then, instead of going to the time domain, you can also directly work out everything in the Laplace domain using this expression. And this is then the expression for your steady-state error for the specific situation. You can also look at the loop transfer function, Ls, which is in most cases much easier. So it is valid. This is only valid, by the way, for unity-gain feedback. And it gives you more insight, and as I said, it is much faster than this operation using the closed-loop transfer function. So for the next examples and discussions, we will only use the loop transfer function Ls for our calculations of the steady-state errors. So, but you can always do that using the closed-loop transfer function. Okay, let's then move on and continue with the loop transfer function Ls. And again, in configuration B. This was our error. So error is equal to the input minus the output. We know output is also given as the error times the loop transfer function, which is actually shown here. And loop transfer function can be composed of several blocks. So it can be a controller, can be a planned and cascade, everything in here in this forward region. This must be unity. That is mandatory to able to calculate this in this configuration. We will do that later for non-unity-gain feedback configurations and then work out those situations also. If I now combine these two, so the error and also the output, you will have now an expression for error in terms of the reference signal and also the loop transfer function Ls, which recognizes that the 1 plus the loop gain is in the denominator, and also we have the input in the numerator. Now again, we can use the final value theorem here, and going directly in the Laplace domain, you will get this expression. And this is the expression for our error. Now you have for unit step input this as an input. Unit step means that your amplitude of your step input is 1. So you can have, of course, let's say 4 or 4t. This can change. But in general, it is most of the time 1 over s. Then your expression here, which is then a general expression, will be then just at the value of r, and you will have this expression. Now for the step, you will work this out. You will get s times 1 over s will be just 1. So 1 over the 1 plus the loop gain. But now I have to, of course, take that limit as approaching infinity, or I mean 0. Then I will place that limit here in the denominator. Now the 1 will not change, but this will change. So I have an expression which will only have an effect on the limit for the for Ls. Now for the unit ramp input, I have again the standard form 1 over s squared. We have seen this in a table a couple of slides ago. And again, using this expression and then specific the ramp input, I have now for r 1 over s squared times s, and then work this out. I will have this expression. So multiply the numerator and denominator by s. I will have this expression. And again, the limit can be placed in the denominator. You can see this will approach 0 because when you approach the s to 0, the term s will be 0, but this will be some value we need to calculate later on. So we have in total this expression, and it will be again simplified to this expression. So in the final form, your ramp input formula will be this. Your step error formula will be then this. The next one is the unit acceleration input, which is the standard parabola input, which was 1 over s cubed from the time representation of 0.5 t squared. So transform that in the Laplace domain. We had this. Again, using this expression, general expression for the error, I go to the acceleration and I put for the r 1 over s cubed, and this is the expression, and moving on as we did here for the ramp input, and again multiply the numerator and denominator by s squared, you will have this expression. And again, put the limit in the denominator terms. This will go again, because of this is then 0. This will leave, that's the only term, and that is then the final form. So we have now 3 expressions, which will give you the error for the unit step input, unit ramp input is the final expression here, and unit acceleration input is also shown here. We will use this later on. This is also called the position error, the velocity error, and the acceleration error. These are all discussed shortly. All right, now we have the situation of static error constants, which is very helpful, and also we will look at the system type. For unit step input, we had this expression. I already said this is a position error, so we had E error for the step. This is now changed to E position. So this is all shown here. So everything with the step, a ramp, and acceleration, we have then replaced it by E sub P, E sub V, and E sub A for the other expressions for the error. And again, for the unit ramp input, we have this expression, and for the unit acceleration, we have this expression. So we will use these expressions to calculate the errors. What you see in the denominator is an expression which we can give it another name, which is then what we call the static error constant. So the denominator terms with the limits determine the steady state error. So these are called the static error constant. Now for the position constant, for this, I have, which is called Kp. We only take this, so without a 1. This one, that's called Kp, capital letter K sub P for position. That's equal to limit as approaching 0 for our loop transfer function. Now for the velocity constant, I have a Kv, and that's then just this. So we take complete expression in the denominator. And also for the acceleration constant, you have this expression only for the denominator. And that will then, using the static error constant, the steady state errors will be then much easily seen as shown here. So the position, the velocity, and the acceleration errors are shown all here. Now in order to calculate the position error, or maybe the velocity, also the acceleration error, you just need that constant, static error constant, and you can then calculate your required steady state error. Now the table here is showing the input here again in a time domain. So U is the step input, and a T is our ramp, and also 1/2 of the T squared as our standard parabola input. These are the formulas. We have discussed this, so 1 over 1 plus Kp, 1 over Kv, and 1 over Ka. I will again remember you that these formulas are also valid if there is no unit step or no unit ramp or no unit acceleration input. You only need to multiply this expression by that amplitude. For example, if your step input is not 1 as an amplitude for the input, but for, let's say, 25, you only calculate this and you multiply by 25 because your input was 25. It's the exact same procedure for the ramp and also for the acceleration. You can see what we have here. We have type 1, type 2, and type 3 systems. Type 0 means, type 0, type 1, and type 2 systems. Type 0 means actually there is no integrator, pure integrator in your system. What does it mean? That your position constant will be, position static error constant will be a constant, some value, not 0, but in any case not infinite. That will of course then give some error, but your Kv and Ka will be both 0, and if that is 0, looking at the formulas, you will have infinite error in the ramp and also parabola. That means for these two you will have infinite error. If your system is type 1, there will be one pure integrator. That means your position static error constant will be infinite. That means your error will be then 0, looking at this. But your Kv will be a constant, so there will be some value which is non-zero, but can be also negative, but it is not infinite. But your acceleration constant is 0, so the error for acceleration will be then infinite. Now, in order to have the Kp and Kv, so the errors for the position, also for the velocity, both are 0, we need a type 2 system which has 2 pure integrators, but the constant now for the acceleration will be some value, and this is then a value which is not an infinite, so that can be negative or positive. Then we have this situation where we can use as a table and recognize what kind of type your system is. Okay, let's now look at an example A, and then illustrate the concept in great detail. So we have so far seen a lot of theory. Let's make it more in numbers. So let's look at the following situation. We have now 3 configurations, 3 transfer functions also for our plant. So this is our plant here. You can see the plant is a little bit changing. This is the exact same as this one, only the s is here added. In this case, the transfer function here is a little bit complicated than this one. These transfer functions first need to be checked on stability. I have done that, and that is all stable. And then we can do the calculation what is required here. So calculate the steady-state errors for each system here if the inputs are unit step, unit ramp, and also the unit acceleration. So actually what we are asked is for each configuration, calculate this 3 steady-state errors. Okay, let's look at the solutions. And for the loop gain, this is the G, which is our plant, and that is in this case just 1. So this is G. It is not mentioned here, but this is G. That is the only block what we have. That means that's also the loop transfer function. So we have a unity-gain feedback system, so we can move on with our formulas for the static error constant. This for position, and if I now substitute the loop transfer function, which is this, and then evaluate this for s equal to 0, I will have 10 times 2 times 3 over 1 times 4 times 5, and that will be 3. That's my position error constant. Now for the velocity, I use this formula. Again, substitute everything in here. What you get is an s times the rest, but if s is 0, then this will be 0. The same is true for the acceleration constant. For the error, this s squared will be then 0, so everything in here is then also together with that is 0, so the result is 0. Now the steady-state errors for this situation only for question A, or the configuration in A. In this case, Kp was 3, so I have 1 over 1 plus 3, 1 over 4. So my error is 1 over 4, so 0.25. For the velocity error, I have infinite because it was 0 for the constant. And acceleration is also, the error for acceleration also infinite because the constant for acceleration was also 0. And this is also what we have discussed about a system type. In this case, there are no integrators in your configurations. So no pure integrated means this is a type 0 system. So everything above the position error will be infinite. Only the position error will be there, and that will also not be 0. That will be some value, and that's given here. So that is the conclusion what we have here. So this is the position error, this is the velocity, and this is our acceleration. Now let's also move on to question B. Again, the loop gain is G, that's just this, and we all recognize that this is a unity-gain feedback system. Again, we start with the Kp, static error for position, and we substitute everything in here. What you see is, since there is an s here in the denominator, this will be infinite. So that's one result. Kv here will be then this. You see a s here, times s, actually divided by s here, so that will go. So you will lose this. They only have this, and if you now substitute in here, s is equal to 0. So that's actually what you first need to do. You divide what you can in the numerator and denominator, and you then substitute the values, the value for s, and you will have here 10 times 3 times 2 over 1 times 4 times 5, and that will be then again 3. So the result here, it will be then 3. Now for the acceleration, again do the same thing. Of course I can cancel this, but I have still one s. That means this will be again still 0. So the steady state errors for this situation, the position error will be 0 because the Kp was infinite. So I have the 1 over infinite will be then approaching 0. So I will not see a steady state error for position for the system 2. That's because it is a type 1 system. There is one pure integrator in it. Now I have error for my velocity. It is not infinite, but it is something because there is a pure integrator. Since I don't have another integrator, this will be not 0, but there will be an infinite error for my acceleration. And these are the result. Again, this is the position error, this is the velocity error, and this is the acceleration error. Again, we start with the position error constant. Again, this expression. The loop transfer function here in this case is again our plant, and this is then this huge expression. What we do first is look at the s's. You just substitute for s equal to 0. You see this s squared will be also 0, so the result here will be infinite. If I move on with the velocity error constant, this will be again the similar expression, but times s. Since I have still one s in the denominator, this will stay infinite. But for the acceleration constant, I have this expression. I will lose these two, so I will lose the s squared in the numerator and denominator. Then I have only 10 times 2 times 3 times 6 times 7 over 1 times 4 times 5. So this actually was shown here, and that will give me 126. Now, we have now the error constant, so the static error constant, so we can calculate the position error, again 0, the velocity error, again 0, because it's all both infinite, but the acceleration error is something, so the 0.008 approximately. So again, the position error, the velocity, and the acceleration. All right, let's then check the simulations here and verify our calculation. First, we start with this system, which is our first system, the question A. Now, let's look at the situation. This is our response to a unit step reference input for open loop. What you see is it approaches 3 for unit step input. And this was our, I call it G1. And this is in the open loop configuration. Now, let's now check also the values here for the response. There are some values. They're over to the 0. The rise time is 1.68 seconds. These are, of course, not what we consider at the moment, but they are nice to have and nice to see here. In this case, the final value is 3, and the steady state error in this case is just 0 because we apply something and we get it. But of course, if you have 1 applied and you want to have 1, you need to change your gain. That is in open loop configuration, of course, a method to do that. But once you want to automate this, you place everything in the feedback configuration. So once we go to the closed loop response, which is much more interesting, and then looking again at the unit step configuration, what you see here is now this is the transfer function response for the first open system, the plant, and this is the transfer function again here, and then Unity-Gain feedback configuration. This was our plant. What you see here, recognize here the final value is 0.75, and we know that we had an error of 0.25, 1 over 4. So this is then the confirmation that this is indeed correct. Again, some values for rise time and the rest. You can see that the rise time and also the setting time has decreased because of that feedback configuration. Okay, that's the verification for our system 1. Again, the error and also the value for our error here from the simulation. So it is correct according to calculations. Okay. Looking to also the unit ramp reference, what we have is the following situation. I have plotted the unit ramp here. This is the orange line, which is a linearly increasing line. You can see that at 20 seconds it's 20, at 40 it's 40, etc., etc. So it's just equal to t, so as a function in time. What you can see here is the blue line is the response. In this case, the difference is something, but it increases and it keeps increasing. So that means if I go to infinite time, so let's say 1 million seconds in the x-axis, I will have more and more and more error between the orange and the blue line. So that confirms also that our error for unit ramp reference is infinite. So that is also a confirmation from our calculations. Now looking at the acceleration input, again, this is the orange line is our input. And again, from this configuration or for this system, the blue line is the response. Again, to emphasize and I'll illustrate that indeed the error is increasing, keep increasing. I have here some value. Let's say at 8 seconds I have 32, and this response is then 23.1, but this difference here at, let's say, 12 seconds is larger, and at 16 seconds it is even larger. So if I move on with my time again to infinite, this will blow up and the error will be infinite, so as we have calculated, and this is then according to calculations. Okay, let's also look at the simulation results then for the second open loop system in our example. Now, the root logistic plot is very important in order to check again our stability. We have done it also for G1 by the way, by plotting the open loop step response, and we have seen that there is no oscillation or blowing up a response. So everything here, you can see the poles at the origin and also some poles here on the left half plane, also 0. So everything is here in the safe region of our complex plane. Okay. Now looking at the closed loop response for the unit step reference, again, we apply here Nonunity-Gain feedback for our G2. This was our G2. What you see here is the following. It is indeed 1. So for a unit step input, the final value is indeed 1. And we have seen that because the Kp, the static error constant for position, was infinite. So it will approach 0 as an error. And that means your error will be 0. And we also see that because the y, which is then the output, is 1. And since input is 1, 1 minus 1 is 0 as shown here. Okay, that's again our confirmation, and again some values for this response, just make it complete. So our error calculation is also correct for this example. Now looking at the unit ramp, what I have done, again, plotted the unit ramp input, the orange line, and also the response, the blue. Again, for this Nonunity-Gain feedback configuration for this plant. What you see is in the beginning, you see the ramp input at 1 second is 1. And at 2 seconds is 2, so it's linearly increasing for the orange line. For the blue line, you can see at 1 it is 0.523, but then it starts to decrease, and then it has a constant difference between the orange and the blue line. So it is more accurate, or the best result which you get is not looking at the beginning of your response, but at some later stage, and then you can calculate what kind of error you have here. So in order to calculate the error, we need to look at the amplitude here, which is 3, and this is then 2.67. So if I now work it out, we of course have calculated it was 1 over 3, which is then approximately 0.333. And when you work out this one, it will be then 3 minus 2.67, which is then from our simulation. It's also 0.33. Of course, it's an approximation, so this is also some approximation due to the limiting accuracy here. So this is indeed, according to calculation, so that is indeed also confirmed with the simulation. Now looking at the acceleration, again, I've plotted for this situation for the G2. The plot, the orange is our unit acceleration, the standard parabola input, and again the blue line for our response. Again, I have labeled some points on the orange line and also on the blue line. Again, you see at 2 seconds it is 2. This is then at 2 seconds 1.24 for the blue line for the response. But this is, or this difference is, let's say 0.76, but this difference is larger. It's 1.1, and this is even more. So it keeps increasing. It's also what we have seen from the calculation, that the error for acceleration will be infinite, and that is now also confirmed here from this plot. Okay, let's then look at the simulation result for the third system, which is then the final one. First, look at the root locus plot, and again, what we see are some poles and some zeros. In this case, we also have determined, because you see the poles start at the origin, 2 poles, and then move up to the left half plane of your complex plane. It is oscillatory at, let's say, a gain of 0.04 approximately. So this will give you the root locus plot. The line which connects your G3, which is your plant, is just a wire, and that has a gain of 1. So there's no attenuation or any amplification. So that's why I'm looking at gain of 1. You can see the damping ratio, and it's all in the lateral plane. That's the confirmation that this is indeed also a stable system. So for this system, it is stable. Okay, this is just checking that this indeed is a stable system, and this is just looking for a situation here. Okay, what we have then is the response first for the unit step input for the closed loop, and this will again see that the final value is 1. Again, the configuration here, so you can see the final value is 1 because there are 2 integrators, pure integrators in the system, and this was our result, and that will mean that the error will be 0. Again, the confirmation, and again some values here for our situation. Okay, now also looking at the unit ramp, and you can see from here, again from the start, I have again plotted the orange line, which is our input, and the blue line is our response for this configuration. And again, at the beginning, you sort of have some error. So you might say, okay, there is some error, but if you look at values later on, so that's actually the steady state condition, of course, you will see that this error will be then 0. So at the beginning, it is something, and it is then decreasing, and at some point, let's say at 1.6 seconds, I have checked here, the response is 1.6, but also the input is 1.6 as an amplitude, so the error is 0. So we have calculated that, and that's also according to calculations. So let's also look at the acceleration, because there we have some error. Again, this configuration with this open loop system, the plant here, what you see is I also begin at the beginning here, so I look at time 1 second, the amplitude 0.5, and the response is very close to 0.491 within the accuracy of your measurement in MATLAB. And then moving on to some other labels, so let's say the input is at 1.4 seconds, this will give me 0.98, and for other values also I have my response. So at some value I have, for example, selected this, maybe this one, you can then calculate your error. Now we have calculated was 0.00794 approximately. This was our calculation. And if I now look at the label here from the simulation results, I can, for example, take this. I say 0.98 minus 0.972, and this will give me 0.008, which is very close to what we have calculated. You might ask, it's not correct, it's not exact. That's true, it's not exact, because this is also not exact, so I also need to check this also a little bit later. But for that I also need some more accuracy in my plot, which is not shown here in this case. So this is definitely correct, and this is confirmation of our calculations. All right, this was the complete discussion of the example about example A about a system where we have seen the effect of the unit step, unit ramp, and also unit acceleration for 3 different systems. We only have considered the reference so far, so we have not included any disturbance from outside. So let's now check that and also discuss the steady state error for disturbance, because disturbances are unwanted input and that enter the system, so we need to also consider that. Feedback, we have here in our configuration, can reduce or even make it 0 the effect of that disturbance at the output. Now disturbance D, shown here, is injected between the controller here in this case. The control is given by C, and also our plant here G. But this can be, of course, anywhere. It can be directly at the output or somewhere else. Now we need an expression that gives also the steady state error with the disturbance included. So it is not only disturbance, it is including disturbance. So we have then an output which will be then, using superposition, a combination of the effect of the reference input and also the effect of the disturbance. And in this case we are not interested in the reference, but in this error. So we can see this expression here. So looking from the error to the output, we consider D as 0. And looking from D to the output, we consider E as a 0, and then you look actually for both cases and add them up. This is then the result from superposition. I assume that this is known. So we can also write this in this form in a really simple way. You can say, okay, the y is just r minus e. And if you now combine these two again, then you will have an expression for r minus e, which is then the left side here, which is equal to the right side here, that's actually shown here. Now, if I now rewrite this, I have this expression, and then expression just for the error, because that's what we want. And now we have an error, which is this. We already know that is 1 over 1 plus the loop transfer function times the r. And this is the second term, which is the additional term due to that disturbance. So using again the final value theorem for this case, you will get this. So using limit s approaching 0, s times this complete expression for EAS, which is actually shown here, you will have this and this. That will give you then the following expression. So I just split for the limit expression for these two terms and add the s in the numerators. What you get is this is our error due to the reference, and this is our error including the minus sign expression for my disturbance. So total error is then the error due to the reference plus the error due to the disturbance including that minus sign. So this is the steady state error due to r, to the reference, and the steady state error due to the disturbance. Add them up, you will have then this expression, again the summation of these two errors. All right, now let's then look at it in great detail, assuming now we can have, of course, many different disturbance signals, assuming it is a step input, so step signal as a disturbance. So d is 1 over s. Then substitute 1 over s in that expression for the ed, which is then this. I will have then this form. So I can also rewrite my disturbance expression in this form. So the configuration here can be also rewritten in this form. And looking from d to e, I see a minus sign that also confirms that there is a minus sign here. So you can actually look from here as an input, and this will be an output, and you will get this configuration. Now, in this case, you add for d 1 over s in this expression. You can see that also here. And everything is just the same. And what you have is then the following. You calculate you work out actually this one. So you lose 1s here and 1s there. So you divide them out, and you will have this expression. If I now also divide the g here from the numerator and denominator, and keep just this minus 1 here, I have this expression. What you see here is the following. And of course, taking the limit in the denominator, you have this expression. What you see is the following. The following conclusions can be stated. The steady state error by step disturbance can be reduced by making this term larger. That's correct, because 1 over a large term is a small term. That can be done by increasing the DC gain of your controller, because once the DC gain is larger, that value will be then of course larger for s approaching 0. Or you make your DC gain of your plant smaller, because 1 over a small value is a large value. So it is or this or that or both of them. That's the conclusion we have here for our disturbance. Let's now look at an example again and make it more precise using some values. Again, we have some transfer function from the plant here. The controller here is given, in this case, is just a pure gain of 100, so just k. We have disturbance, and we have also the reference here. Now let's then calculate the steady state error due to that unit step disturbance. So d is again 1 over s. This is the formula we have seen in the previous discussion, previous slide. If I now use what I have for g, this is the g, the plant, and I have also the limit for the controller, just k, then we have the following situation. So work it out here, you will have this. If I now evaluate this at, or approach, let it approach to 0, this will go. So that will be then minus 1 over 0 plus k. So this will be then minus 1 over 100. So it is minus 1 over 100 minus 0.01. That is the error due to the unit step disturbance for this configuration as an error. Okay, that means the following. Making a controller k larger will reduce the steady state error due to the step disturbance. So that is a conclusion we also can draw from this situation, because the k is now 100, but if that is, for example, 1000, this is then 10 times smaller. If you make it million, and it will be even more smaller. So it is inversely proportional to the value of your controller gain. And that is good, because making a gain larger will make the effect of the disturbance smaller. In this case, it will be never zero, but it will be much smaller when you increase your gain. Okay, let's now also look at the steady state error for non-unity gain feedback configurations, because control systems often have that. It's not only just a wire from the output of the summation point of the configuration, and the controller in the feedback loop can be also there. So there can be a controller in the feedback loop, and there's also some physical systems, let's say a transducer element, a sensor in the feedback loop. So this is a much more practical situation. And general system configuration, controller, implanter, and transducer is shown here. Again, the disturbance, the reference, the controller, the sensor, and the plant. And in this case, you see directly this is not a non-unity gain feedback. So this is not a unity gain feedback configuration. The controller can be also here. So we can also say there is no sensor, just a controller here. That's also possible, but still non-unity gain feedback configuration. So how do we work this out? The easiest way to work this out is using the knowledge we have from our unity gain feedback system. So that means convert this system to a unity gain feedback configuration. How is it possible? Now, let's say the disturbance is 0, so we assume there is no disturbance. We multiply the plant and the controller, so let's make that just M, and then keep that H also in the feedback loop, and then move this in this configuration. What I have done is the following. The M is still the cascade combination of the controller and the plant here. The H here is still in place. What I have done is, in order to have a unity gain configuration, I have added here a -1 and a +1, because that's 1, this wire is just 1 plus 1. So together they are 0, so there is no connection here. But the improvement, or the additional value we have now, the following. Since there is a unity gain configuration here, I only need to make an approximation, and make a simplification for these 3 blocks. So, excuse me, that went away. So that means this arrow will be then making this simplification. So you have that H -1 together as a block. That will be then again taken together using Mason's gain rule. And then we have only one transfer function. And this is then the transfer function we will then use. That is then ms, which is then the forward path, over 1 plus the loop transfer function that's actually shown here. ms over 1 plus the loop. And loop is ms times hs -1. And now we can use this as the loop transfer function for this situation in order to calculate the errors. So you cannot say in this case by only multiplying the G, the C, and the H, and then say that's my loop gain. That cannot be done in this case if you want to use the formulas we have discussed so far. Okay, so this is now a unity gain feedback configuration. Now, let's also look at the sensitivity in great detail. These are changes what we have in our system. So we have some system parameters, let's say a time constant of your system, or maybe a gain of your system. It can have an effect on your system behavior, but how much effect do we have? How can we make this more precise and quantitative? That's actually the topic of sensitivity. So parameter changes due to heat, humidity, aging, or other effects can have some effect on your system. Now, parameter changes should not be have an appreciable effect on system performance. So again, this must be quantified. So how much effect do we have? Now, the greater the sensitivity, the less desirable the effect of a parameter change is. So if I just change for example, the time constant of my system by 1%, and if that has an effect of 10% of the output, that is indeed not what we want. So the ideal system has zero sensitivity, so it is not sensitive to any parameter changes, which is of course not true in practical situations, but that's an ideal situation. That means changing your system parameter will not have any effect on the transfer function. So we actually talk about this in terms of transfer functions. So definition 1 is sensitivity. For the sensitivity is a degree to which changes in the system parameters affect system transfer functions and hence the performance. So that is how much there is an effect due to the change in your parameter. The second definition is also used is the ratio of the change in your transfer function to the change of your parameter for a very small incremental change. It is not valid for huge changes. So if you go, for example, in your time constant, let's say 200% change, that is not the situation where we're talking about. This is for our small changes. So these two definitions are handy to use to understand the sensitivity. Now this is the formula, more formal formula that states the sensitivity. The sensitivity is given by capital letter S, and the transfer function, the total transfer function, let's say this T, and the parameter is P. So this is the general expression which relates the sensitivity of your system T to the parameter P, and which is then given by this. Again, you can see the delta P, which is a small change in your parameter, must approach 0. So this is the definition of the differentiation. There's a change in your closed loop transfer function divided by the change in your parameter, and that will be then given by this expression, and then that will be then in the limit defined as this. So P, small letter p over t, times the partial derivative of your t towards the small letter p, which is the parameter here. And that will be then used for our calculations for sensitivity. It is a partial derivative because the t can be also dependent on the controller gain, can be dependent to another parameter, so it is not just only p. All right, and again, small incremental changes. We don't forget that. Let's look at an example, example C, which is a very practical situation, and you can see from this example that indeed feedback has some effect of our sensitivity. What we see here is actually the following. We have an open loop gain configuration. So there's a voltage amplifier with a gain of minus K. So it is an inverting amplifier. It is an input V in and V out, but it is an open loop. So every small change will have an effect directly at the output. And this is the negative feedback configuration of that same amplifier, but then in this negative feedback configuration with R1 and R2. And R1 and R2 will cause some voltage fed back to the input, and that is then given by this ratio. And this configuration is actually an inverting amplifier, which you know maybe from op-amp circuits. Now what we want to calculate is the following situation. This is the open loop, this is the closed loop, and we will like to compare them later on. But first calculate the sensitivity to changes in the gain K of this amplifier in the open loop and also the closed loop configuration. That means the following. Now, let's look at the situation. First, open loop, there are no feedback elements in it, so just open loop, V in and V out, and the gain in between. Now, the transfer function then is V out over V in, it's just minus K. We already see that. Now, sensitivity, again, the formula means the sensitivity of the transfer function for the changes in the K is then given by this expression, again the partial derivative of that transfer function to K, but we know this T is only dependent on K, so we don't have to use a partial derivative, but if you do just the derivative, that will give you minus 1. And if you combine these, and you also know the expression for T here, you will get this, so K over minus K, because that's T, times minus 1, and that will just plus 1. That means the following. Whatever you do with your gain, your sensitivity is 1 as a scalar value. That means 100%. So every change will be reflected as 100% at the output. This is of course a huge sensitivity. Now let's also do that for the closed loop with feedback and check the results. Again, the transfer function. This is the transfer function, the output divided by the input voltage. That is then a minus k over that 1 plus the loop gain, again using the similar formula we know from op-amp circuits. Now this is for our transfer function. Now for the sensitivity, again a similar formula. This one, again the same here. And now we differentiate again the t, the closed transfer function, towards k. In this case, we need to use the rule for fractions. So the coefficient rule, so that we have actually this one, so you square the denominator and then make the calculation for the denominator also. The result is this, and if you now add them up, you will get this expression. So k over the transfer function itself times the derivative of that t towards k, the partial derivative. If you now simplify this expression, you will get 1 over 1 plus the R2 over R1 times k, so 1 plus the loop gain again. All right, this is then the result, and that means the open loop and the transfer open loop and the closed loop transfer functions and closed loop configurations show the sensitivity. What you see is making k larger will make, of course, the sensitivity smaller, given some value, of course, for R2 and R1. But this is always 1, so we have always 100% sensitivity here. This can be different. Now we will then compare that, comparing the sensitivity of the open loop and the closed loop configuration. Now let's take some value. Let's say this is the ratio for this one is 0.2, and also that k is 1000, for example. What we have is then the following. We get, just substitute the value in here, you get 1 over 1 plus 0.2 times 1000, that will give you 1 over 201, which is approximately 0.005. And that means it is actually only 0.5%, of course, using these values. So 100% sensitivity in the open loop has decreased by just using feedback to 0.5%, of course, using these values. This is a huge improvement, of course, looking at the open loop configuration. So sensitivity is reduced by 1 plus the loop gain. That is actually a general rule in amplifier design also. But let's look at it in great detail. So first, collect all the values that we have for our closed loop system using feedback. And then again, taking this ratio for R2 over R1 as 0.2. Now let's then check the effect of the open loop gain, because I have, of course, said it is 100, and then we have some calculations done, but I also do that for other calculations. What we have is then the following. You can see here for 10, so it is a small value now gain. The closed loop gain is now minus 3.33, which is then this expression I have used using 0.2, and sensitivity is here 0.33. This is then the e to the power 10 to the power minus 1. But when I increase it to 20, you can see this is then, let's say, exactly minus 4 in this case, and you can see it is now 0.2. So sensitivity is decreasing. If I make it now 100, I have my sensitivity value of what we have just calculated, and I have now also the gain. This is approximately 0.05. Okay, now what I have here for 1000 is again what we have here, and if I increase it even further, 10,000, 100,000 and a million, you can see the sensitivity is decreasing. And what is also interesting is the closed loop gain is also approaching the value of minus 5, which is actually the inverse of that one with a minus value. That is the actual gain of an inverting amplifier. But more importantly is the sensitivity. Sensitivity is almost 0 when this open loop voltage gain of your amplifier is becoming larger. Now in actual op-amps, this is most of the time, of course, in a couple of millions, maybe 10 million, maybe 100 million for open loop gain. That is really required to have a very small sensitive value for your feedback amplifier. And this is a good illustration, I think, for the sensitivity in a practical sense. So sensitivity gain reduces by 1 plus the loop gain, and again seen here in the table. And loop gain is k times R2 over R1 for this configuration. Okay, Let's do now several examples in part 2. So moving on to the example number 1, what we have is a transfer function of a plant, shown here, and we also have a negative feedback, and there's a control in the feedback in this case. I would like to calculate the steady state error if for a unit step input if this is a value of 3. We don't have a unity-gain feedback configuration, so we need to change this to a unity-gain feedback configuration. So let's first say, okay, I don't have a unity-gain feedback configuration. Let's first start with that. So that can be redrawing. And again, we have discussed this. So make a -1 here and a +1. So we have two branches here. And then simplify this using Mason's gain rule. This part, which is then called P, I just call it P. So it's just P. You will collect them together and you will get this expression. So this is the P. Okay, the P here is the plant over 1 plus the loop gain, which is then the G times the K minus 1, which is shown here. We need to use this as our actual loop gain for our error calculations. Now you just substitute the values for the plant and the rest. For the K also, you will have 10 over S plus 24. So again, remember it is not G times K your loop gain for the steady state error calculations. It is using this approach. Now for the unit step reference input, that's actually what is here. I can use this static error constant formula. Again, P as my loop transfer function. I substitute everything in here for S then for equal to 0. Will be 10 over 24 or 5 over 12. That will be then the value for my Kp. Then what I have is then 1 over 1 plus the 5 over 12 is then 12 over 17, approximately 0.706. That's the value for the error. That means then the output value, the steady state output value, then R minus the error. That means then 1 minus this will be then 0.294. That's the result from the calculations. So let's check that in the simulations. So we give the open loop and the closed loop response. Open loop is the blue. You can see the G, and the closed loop is the orange line is the T. You can see this is much smaller. There's some error here. And we know that the value here was 2.5, because if you calculate the DC gain of that system, you get 2.5. And here you get that 0.294, which is our final value we have calculated. So from the calculation, we had an error of 0.706, and the input is 1. So R is 1, and Y is that output. So that is indeed the error we have, and the calculation and the simulations do confirm for this first example. And you also see that the settling time and also rise time is much smaller than the settling time and rise time of that actual system. So in total, given also that information, you can see that this is a faster system. But there's a steady state error, so that's a problem. Continuing with example number 2, we have now another transfer function, a second order system plan for the plant. In this case, we have the controller and the feedback. What we want is the calculation of the value of K if the steady state error is 0.4 when the unit step input is here at the reference. So we need that 0.4 for AEP, so error for the position must be 0.4 for the unit step input, and calculate the K given this plant transfer function. So how do we start? Again, we know this system is non-unity-gain feedback, so first we need to change that. We have done this in the previous examples, so we can move a little bit faster and use the Mason's gain rule here. Again, denote this, for example, as P, as I did also in the previous examples. P is then this, so again, forward divided by the 1 plus the loop. This is an expression. Now I can substitute now also the plant transfer function here, and this will then result in this. So this is a simplified expression here where you see directly that the K is indeed an unknown. Now I know for the unit step reference input that the Kp for my position error constant is this, where the loop gain is now just P, and that's then 40 over that complete expression in the denominator. That will give me then 40 over 12 plus 40 times Ky is 1. This is what I have for Kp. Now what do I know for my error? I know the error is 1 over 1 plus Kp, because it's a unit step, I just have 1 here. Kp I know, which is an expression, so I can substitute that, and I also know the error, which is 0.4. So it is actually 0.4 equal to 1 over 1 plus the Kp, which is then this expression. You can see in this expression, the final form, that there's only one unknown, which is the value of K. If I just calculate this, it will be 41 over 30. And that will be approximately 1.367. That's the required gain if you want an error of 0.4 for the unit step input or for this situation. So the steady state value of the output signal will be then, using again the similar formula, y is output is equal to the reference minus the error, and that will be then 0.6. So we will need, or we will see in the simulation, if this calculation is correct, that the output is 0.6. So let's check that in the simulations. Again, open loop in a closed loop system response. This is the open loop configuration. The blue line is again a response. You can see 40 over 12 will be then 3.333 or 10 over 2. I mean 10 over 3. And I have also the value here for my closed loop system. So the R is also the yellow line, that's input. So it is then amplitude is 1. And you can see the final value here for, again, the open loop is 3.33. But the final value of your closed system using this gain is 0.6. That is indeed what we had, because our error was given by this. And now minus 0.6 is 0.4. That is indeed correct, what we have calculated. And again, here some values to compare the open loop and the closed loop orange line. And you can see again that the system is faster, but now we have some overshoot, but it's of course a discussion besides this topic. Okay, moving on to the next example number 3, which is the final example for this video. In this case, we have two transfer functions given, a little bit different. Now we have a plant here, again second order, but now also the sensor here, which has some dynamics, not only a gain. In this case, we will also like to calculate the steady state error for unit step input. Again, non-unity gain feedback. And we need to again adjust this in this format. So we have the sensor and the plant. So sensor again in parallel with the -1, in parallel with the +1. And then taking this using the Mason's gain rule as a controller P. Again, we have seen this, so we can now speed up the system. This is the H here instead of K now. And then working out this. If I now substitute everything I have for my G and also for my H, I have this, and simplifying this, you will get this expression. Now we would like to calculate the error. That means I need an expression for my error. For that I need the error constant. This is the error constant. The loop gain is exact P, because I have now this as P, and P goes now times 1, the unity gain feedback configuration, and I can use this formula. And again, this is the expression. If I now work this out, there will be minus 1.5. So everything here and here, S is equal to 0. This will go, by the way, completely. Only this, I mean this part. I have 100 times 3, so 300 over 100 minus 300. So it is the 100 over, 300 over minus 200. That will be then minus 1.5. And this is interesting result for Kp. So then we have then the following error, 1 over 1 plus Kp, again unit step input, that's why it is 1, and then it will be 1 over 1 plus minus 1.5. This will be then minus 2, interesting. So we have an error of minus 2. What does it mean? We will see that shortly. Steady state error or value of your output will be then I is equal to R minus the error. That means then 1 minus 2 will be 3. This gives actually the following conclusion. The position error is negative, thus the steady state value of your output is larger than the input. That can be the case. That's still, of course, a steady state error, but it's now larger than the actual input. So larger or smaller, the error is still there is an error. The position error is not 0 because a pure integrator factor, which is interesting because we have an integrator factor here, and we have said that it's a type 1 system, but using this dynamics here in the feedback, the complete dynamics has changed considerably, that this pure integrator will not cause a 0 steady state error for position input, for unit step input. And that's interesting situation, and that's why I have chosen this example to illustrate that this is not just that like, okay, I have one pole at origin, complete the rest of the system is something, so I have guaranteed that my error will be 0, which is not true as we see here. So let's now check the calculations, the simulations also, and then confirm our calculations for example number 3. This is the plant and also the sensor, and these are the transfer functions. Again, I have plotted the reference, so which is our step input. Again, you can see it is just one amplitude, our orange line, and the T is our response, is the blue line. Because it has a large overshoot, but that is a discussion of course aside. I see a final value here of, again, the reference, but I also a final value of 3. And this difference is indeed 2, but it is of course above. So R minus Y is then minus 2. So that is indeed, according to the calculations, that is correct. So this confirms the calculations in a nice way. And you can again see the steady state error means that there is an offset between the reference which you command and the response actually. It can be higher or lower. That means the exact same. It is still an error. All right, this was about the steady state error theory and also the sensitivity, using several examples to illustrate the concept of non-unity gain, unity gain feedback configuration, and also effect of system parameter changes to your transfer function of your complete system. I hope this clarified the situation for you about this topic, which is very important, the steady state errors and also other configurations for the controller in order to calculate this, and also then choose your required controller. If you have any questions about this video tutorial about this topic, please let me know and I will try to answer them as soon as possible. Thanks for your cooperation and see you next time. Take care.